Welcome everybody to the third discussion meeting of 2025 and our discussion meeting here at conference. For those of you who I haven't met or don't know me, my name's John Aston. I'm president of the RSS this year, and it's a great honor to be able to chair this discussion meeting. This discussion meeting is sponsored by the Society's research section and the Discussion Meetings Committee. We're going to hear about the paper Augmented Balancing Weights as Linear Regression by David Bruin-Smith et al. The meeting's being filmed, and the recording will later be posted on YouTube. We'd really like to encourage people to make even a brief comment on the paper. This will be announced at the start of the open session following the presentations. There'll be David's presentation and then a proposal and second for the paper itself. Anyone who'd like to comment will have up to 5 minutes to speak. All comments can be written up afterwards for the journal, up to 400 words, and will be published with the paper in the journal. Just as a note, we won't be using the app during this session. We really want people to be able to do it with their affiliation and their name, so we would encourage people to step up when you come up to speak, say who you are, where you come from, and we can discuss the paper that way. And that way we can record who it is who's making the comments and encourage you to write them up for the journal. So without further ado, I'd like to introduce the paper. So the paper, Augmented Balancing Weights as Linear Regression by Bruin-Smith, will be published next year in the Society's Journal Series B. So with that, I'd like to welcome David up and give his presentation. Thank you, David.
Okay, thanks everyone. Thanks for coming to the discussion session. The paper's called Augmented Balancing Weights as Linear Regression. That title was a product of a particular time and place, and I'd probably use a different title now, but we'll get into that. If any of this is interesting to you, you can reach out to me at my personal email address, causal@stanford.edu. And I had 3 wonderful co-authors on this paper, Avi at Berkeley, Betsy at Johns Hopkins, and Oliver at Ghent. So my personal motivation for starting this project was from my applied work, which is at the intersection of causal machine learning and macroeconomics, where we might have an empirical question, like if a household receives an unexpected check, how much do they spend versus save? So you have a household that makes a certain income, they have a certain amount in savings, they receive some unexpected money, what do they do with it? So I have access with some collaborators to a large Icelandic tax data set where we observe lottery winners, which is sort of plausibly random variation in income for estimating causal effects. You can fit some crazy complicated machine learning model like a gradient boosted tree ensemble to predict spending, and then calculate some policy relevant summary statistic like an average spending response. And this works great. It's relevant for problems like fiscal stimulus, but there's an issue, which is we have a bias variance trade-off. So we don't want to overfit, so we constrain the complexity of this tree ensemble in some ways to generalize well out of sample. But that means even asymptotically, we have a biased estimator. So we are not asymptotically normal. You can't get a confidence interval in the usual way. And if you're calculating something like an average treatment effect, that's just a single number that you want to report to policymakers or economists, and they really want a confidence interval. So in general, this talk will be about so-called debiased machine learning, where we do something like this, we compute some really complicated model, we calculate some summary statistic, and at the end of the day, the goal is to get an unbiased estimator with a confidence interval. So if you take anything away from the talk, that's something that you can do. It's called debiased machine learning, and it's really useful. But we'll get into a lot of details beyond that. So there's many proposals for doing this type of debiasing. We consider a recent class that's really been exploding in popularity, especially in econometrics, where it's called automatic debiased machine learning. But I came from out of a statistics tradition where this was called augmented balancing weights. So that's the title that I used. And our goal was to try to demystify the behavior of these estimators on real data and in finite samples. So let me give some problem setup. Consider 2 distributions, P, which is, let's say, a treated group where we observe covariates X and then some potential outcome Y1. And then we have a whole population Q where X is observed, but those potential outcomes Y1 are missing for the control population. This is a totally standard causal inference setup, so if you're from the causal inference community, this will make sense right away. But more generally, this can be sort of any two distributions, P and Q, where you observe X, you observe Y and P, and you don't observe Y and Q. So any missing data problem will have this setup. It doesn't necessarily have to be causal. It doesn't have to have these parentheses ones running around. And our estimand is going to be the missing mean in the Q population. So again, in causal land, this is what you would do to estimate the average treatment effect, but we can consider things more general than that. So how do you use machine learning to do this? Well, we have a missing data problem, so we can do imputation. In this population where we observe both X and Y, we can train a model to predict Y given X, call it M hat. And then we can predict in the whole population, filling in those missing values, and we can take the plug-in estimate, which is just the sum, the mean, the sample mean of those imputed values. So let's stop here. I use the stop sign in talks whenever there's more nuance in the original paper. I come from California, and both California and Scotland have stop signs. But there's a sign that I've seen a lot in Scotland, not so much in Edinburgh, but in Scotland, that we don't have in California, which is this one. So I'm going to use this whenever there's a nuance in the paper. So in particular, in the full paper, we don't need to have a binary treated control. We don't have to be estimating a simple sample mean. We can tackle high-dimensional continuous treatments with high-dimensional continuous covariates. Also, any linear functional estimand will do. But for the presentation, it's way easier to just have a simple treated control and be estimating the missing mean. So we're going to start by talking about how machine learning introduces bias. We're going to have one solution, which is undersmoothing, another solution, which is this debiased machine learning idea. So MHAT is biased because our prediction models are always regularized in some way. We constrain the complexity to generalize well. And I'm going to consider the class of regularized linear models, so things like Ridge or Lasso, where we estimate a predictive model that's linear in X. This could be a transformation of the original covariates. So it could be a transformation that's really high dimensional. It could be infinite dimensional in the case of an RKHS. It could be the embedding from a large language model. My personal favorite is to fit some type of tree ensemble and then use the output of each tree as a basis. And you can run ridge regression on that. And then actually, in applied work, it usually works pretty well. So this is all to say that it doesn't have to be linear in the original covariates. This is a pretty broad class of estimators. And I have the schematic for understanding what's happening when we do regularization. So as our regularization parameter goes to 0, we fit y minus x beta as much as humanly possible, and we get beta hat OLS, the unregularized estimator. As we regularize more, we fit less and less, and then the in-sample residuals y minus x beta get larger. So note, if you're using some type of transformation, like an LMM embedding, then this OLS is the OLS coefficients in that transformation. If D is bigger than N, then our results hold for the minimum norm in turbulent. So that could be really exotic. If you have some crazy high dimensional basis, this OLS could be a very exotic estimator. But that's what I mean when I say OLS in this talk. It's the unregularized linear model. So regularization bias means that we have larger residuals. When we plug that into the sample average, that passes straight through. So the sample average doesn't get rid of any bias, even though it shrinks variance. And then that means that we're biased for our target estimand. As a result, the estimator is not asymptotically normal. That means we don't get the usual standard errors. In applied work, that's usually what I care about, that my confidence interval isn't valid. But also it's possible that the optimal bias for prediction might just be bigger than the optimal bias for the mean. So there's some sense in which a sample mean is much simpler than a full predictive model, and so maybe it needs less bias, even from a mean squared error point of view. So machine learning is biased because these residuals could be bigger than they possibly could be in sample. One solution is just to fit more. So use a smaller degree of regularization, lambda prime, that's going to give you a solution that's mechanically closer to OLS, the unregularized estimate. Another solution is to correct for the residuals after the fact. So you do the plug-in of x beta, and then you add this bias correction term. And the central result of our paper is to show that you can always rewrite this debiased estimator as a new plugin, x beta hat aug, which is also mechanically always closer to beta hat OLS. So there's some sense in which these two approaches, which both have like massive literatures behind them, are really kind of doing the same thing. In general, I find this to be a very useful conceptual framework. So the fact that you can take this debiasing and always think of it as unshrinking towards the unregularized estimate is really useful for thinking about hyperparameter tuning, for example. But we have many other downstream results, including connections to the machine learning fairness literature, benign overfitting, synthetic controls, and more. So this has been a useful, it's like a fruitful structure for getting future results as well. So let's start with talking about undersmoothing. So if we go back to our regularization schematic, we originally fit some, let's say, a ridge regression model or whatever, where you have some regularization parameter lambda that you usually pick by cross-validation. So you just pick the lambda that gives you the best cross-validated predictions. Undersmoothing says, OK, choose some lambda prime that's smaller than that. So you take the cross-validated value and you, I don't know, divide by 4, something like that. Use less bias, like mechanically, you'll have less bias. And there's a huge literature using this, especially in theoretical results. And we've seen recent work, actually, considering undersmoothing quite seriously. Just as a note on the name, this literature is usually about bandwidth choice for some type of kernel. That's why it's called undersmoothing. But the more modern word would be overfitting. So we're intentionally overfitting so that we have less bias at the cost of more variance, but that's intentional. So the question when you try to do this in practice is, well, what lambda prime do you pick? And here we have a wonderful quote from Bruce Hansen. It is unclear how to pick this suboptimal hyperparameter. I call undersmoothing a dirty trick because it is slipped in by authors to make their results cleaner and derivations easier. I'm not sure I would go that far, but suffice to say, it's hard to use in practice. Like, you have to do something. Maybe it's divide by 4. You have to pick lambda prime somehow. So another solution is to do bias correction. So debiasing just takes the plug-in estimate. So we cross-validated our regularized model, that's beta hat lambda, and we add a bias correction term for the residuals. This approach goes back to at least the 90s from the so-called AIPW estimator. But recently in econometrics, this has been called the double debiased machine learning approach. And if you compare to what we were doing in undersmoothing we were mechanically making the residuals smaller. Uh-oh. I lost visual on my screen. Oh, it's back. So we can mechanically make the residuals smaller. In double debiased machine learning, we just add this correction term for the residuals. The key is that we correct for the residuals only in a particular direction, which is called the inverse propensity weights, or the rate on Nikodym derivative, or the Reese representer. These are all names for the same thing in this type of setting. So I'm going to review what that special direction is now. This will be easier for those of you who have seen IPW before, but I'm going to do my best for the general audience. So IPW, you can think of these as the weights that make P look like Q. So for any function f of x, when you reweight f with w under P, the mean of that is equal to the mean of f under Q. So sometimes this is called the population balance property. For those of you who really like Hilbert spaces, do we have any Hilbert space fans in the audience? Oh, I saw one hand. Oh yeah, multiple hands go up. That's not what I was expecting. That's great. This should look a lot like the definition of the Reese representer because it is. And we talk about that in our paper. Other papers have also made this connection before, and that's useful for generalizing these results to generic linear functional estimates. So in particular, these weights make P look like Q, and the most useful one that they could use to make P look like Q is the conditional expectation, y given x. That's what's going to make this do debiasing for our plug-in estimator. And it turns out that these weights have a known closed form, which is 1 over e to the x. That's why they're called inverse propensity weights. E to the x is called the propensity score, and it's the probability of being in group P conditional on x. And the standard thing to do that the papers in the 90s would do is fit e hat of x, so estimate the propensity score, and then invert it. So you get your weights W by taking 1 over e to the x. But this is often horribly unstable. So if e to the x is very close to 0, any estimation error is going to get blown up. You end up with an enormous variance. And in high dimensions, you can actually just sort of theoretically show that this will always, like virtually always happen when you're in really high dimensional settings. So there's an alternative strategy, which is called balancing weights, which just says don't invert e hat of x, just estimate w hat directly. So we're not going to do traditional IPW in this talk. We're going to use balancing weights where we fit w hat directly. And this approach goes by many names. It's been reinvented many times across many different literatures, and I think that's just because it's fundamentally a good idea. In the survey literature, it was called calibration weighting. It's been called synthetic controls. In computer science, it's called direct density ratio estimation. In the statistics literature I came out of, it was called balancing weights. That's why I call it balancing weights. But then there's also this econometrics literature on least squares, sieve, Reese representers, the automatic estimator, and Reese regression. I like the Reese regression name a lot. I probably would have used that in the paper, but we wrote it before I heard that word. So, okay, so how do balancing weights work? Well, what we're going to do is we're going to enforce this condition directly instead of using an analytic form. And in order to numerically enforce this condition, we have to choose some function class f just to make this sort of numerically or computationally tractable. And our constraint on the function class is that hopefully it includes this conditional expectation. That's what allows us to do debiasing. And linear function classes have this really especially nice form where you just have a difference, basically a difference in means. So you have the reweighted treatment covariate mean over here, the full population mean that you're trying to target over here, and then you measure that imbalance in your favorite norm. Maybe it's the 2 norm or the infinity norm, et cetera. And that gives you a nice numerical optimization problem. You have this imbalance term. You then regularize the weights, so that's what that delta w squared is, because again, we want this to generalize out of sample. And there are many, many, many variations of this problem that have been used across many, many literatures. You can put different constraints on w, like a non-negativity constraint. You can do different choices of regularization scheme. In this paper, we fix the optimization problem looking like this and just consider different norms for this imbalance. So as a brief terminology break, what do we call these balancing weights estimators? Well, in outcome model land, we use ridge to refer to L2 penalized models and lasso to refer to L1 penalized models. If you use an L2 penalty on the weights, that through a duality result corresponds to L2 penalized weights. If you use an L infinity penalty on the weights through a duality result in our paper, that goes to an L1 penalized weights. So if I say lasso for the weights, I mean use an L infinity norm on that imbalance. If I say ridge for the weights, I mean use an L2 norm. Oh, my monitor's back. So delta means that there's another bias variance trade-off. We control this degree of regularization. As delta goes to 0, we're going to perfectly balance the covariates. And as delta gets bigger and bigger, we'll have lots of imbalance, and then that's going to be a source of bias. So this bias correction combines these two different models. We combine our outcome model, beta hat lambda, and we combine our weighting model that we fit with balancing weights in this combination. And again, this has been proposed many, many times with widely varying names. In the survey sampling literature, it was called the G-reg. This is exactly the numerical setup that was used in the debiased lasso paper. This has been called approximate residual balancing, augmented minimax linear estimation, augmented synthetic controls, or automatic debiased machine learning. All of these are basically doing this exact same setup. So this has been pretty popular, especially in the last 5 years. So our new result is going to be that when you do this debiased machine learning with balancing weights, we're going to relate that to undersmoothing. So here's our debiased estimator. We have a linear, regularized linear outcome. We have balancing weights that balance linear functions. This is equivalent to a new plug-in outcome model, beta hat aug. And this beta hat aug has a very particular closed form. It is an element-wise convex combination of your original regularized model with the unregularized beta hat OLS. And this A delta depends on how well you solved the balancing problem in sample. So A delta is how much did we balance. So this top one is the reweighted P, the bottom one is the mean and Q, which we were trying to make look the same. Because we were trying to make the top one look like the bottom one, I'm going to use the notation xq hat versus xq bar. And then we can mechanically walk through the edge cases of what happens here. So this A delta is controlled by this degree of regularization in the weights. On one extreme, when we don't regularize the weights at all, we get xq hat equals xq bar. That means A delta is equal to 1. And our estimate just is the unregularized estimate. So no matter what we do with the fancy, maybe you did some crazy high-dimensional elastic net, if you don't regularize the weights, you end up with the unregularized estimate. So this is a well-known result. There's a paper that goes back to Robbins et al. 2007 with the catchy headline, OLS is doubly robust, and this is one example of that. It turns out that the beta OLS estimate can always be written in terms of this debiased estimate, and you can think of our result as a generalization of that, that it's not just this one extreme. We have this way of writing the debiased estimate as a continuum of OLS to beta hat lambda. On the other extreme, as delta goes to infinity, you regularize the weights away, and so you don't do any bias correction, and you just recover the original regularized outcome model, beta hat lambda. In general, you have to pick delta somehow. Usually you do it with some type of cross-validation scheme. I'm going to talk about that in a bit. And you end up with some delta that's between 0 and infinity. So you get something that's mechanically closer to OLS, but not all the way equivalent to OLS. So how does this compare to traditional undersmoothing? Remember, in the undersmoothing literature, we just pick something mechanically closer to beta hat OLS. How is this beta hat lambda prime related to the debiased beta hat aug that we just introduced? Both move towards OLS, but do they do it in the same way? For L2 regularized models, it turns out that these things are identical. So here I'm writing the form, this is the famous form of ridge for diagonal covariance matrix, where you can see it as a sort of shrunk version of the beta hat OLS. If you combine beta hat ridge with an L2 penalized weighting model, you get beta hat aug that looks exactly the same as another ridge model. But you have a different tuning parameter, gamma j, that depends both on delta and lambda, and it's always less than or equal to the original lambda. So we've just recovered classic undersmoothing in this ridge setting. And our mnemonic for this is ridge plus ridge equals ridge in debiasing land. So let's go back to this quote from Bruce Hansen. Why was undersmoothing so hard? Well, we didn't know how to pick lambda prime. We picked lambda with cross-validation, but how far do you go when you're undersmoothing to get rid of your bias? And our result says that in this ridge case, at least, this is all equivalent to picking this other hyperparameter, delta, that controls the weights. And we use this to try to explore hyperparameter tuning for delta. So one of the ways in which we do this is through RKHS asymptotics. There's probably not enough background on this slide to walk through this in a reasonable way, but one way of saying this is that there's a lot of work that considers combining two ridge models in a debiased form that has a hyperparameter that goes to 0 at rate into the -1/2 for both the weighting and the outcome model. There's a whole separate literature that considers undersmoothed ridge models in RKHS, and they use a hyperparameter that goes to 0 much faster, so 1/n. But our result shows that this thing on the left can be written equivalently as a single hyperparameter that goes to 0 at 1/n. So there's some sense in which these two totally separate literatures are using the same analytical basis. But there's something super useful here that we noticed, which is in this undersmoothed kernel ridge literature, we never did anything specific. We never talked about weights at all, necessarily. And one way that mechanically you can always get a gamma or a lambda prime that goes to 0 at 1/n is just to set lambda equal to n to the -1/2 and then set delta equal to lambda. So this is a kind of cheat code. You do your ridge regression, you cross-validate lambda, and then when you have to choose your weighting hyperparameter, you just use the exact same value. So we compare 3 different approaches for tuning delta, including the just choose delta equals lambda. We cross-validate the imbalance. We cross-validate something called the Reese loss, which came out of the econometrics literature that I'm not going to describe, but this gives you a different value of delta in general. And all 3 of these approaches are reasonable. They all have motivations. Cross-validating imbalance sort of controls the worst case bias. Cross-validating the Reese loss targets convergence of the weights. And if you choose delta equals lambda, this is suggested by the RKHS asymptotics that we just went through. But in simulation, none of them strictly dominates the other. And in fact, in some theoretical results, we can show that none of them, you can always construct a DGP where one of these does better than the others. So I'm just going to do an illustration of what that looks like numerically to show maybe like the stakes. How different can this hyperparameter tuning, how different can the result be? On the y-axis, I have our debiased point estimate. On the x-axis, I'm just going to scroll that delta, the regularization parameter for the weights. So delta is what's on the x-axis. And we get this blue curve of results. At the bottom, as we move delta to infinity, we asymptote to the just plug-in ridge model. At the top left, where we have this triangle, that's the OLS unregularized point estimate. This green dotted line is cross-validating the L2 balance. You notice in this particular example, that actually collapses, just giving you exactly the OLS point estimate. The red dotted line, you cross-validate the Reese loss. It gives you a very similar point estimate. And if you just use delta equals lambda, you get this point estimate. And these, this is a reasonable amount of variation. This is between $2,100 to $1,700. So this does matter how you pick this hyperparameter. It gives you pretty different results. All of them are much closer to OLS than they are to your original biased estimator, but it still makes a difference in the interpretation. So to try to resolve some of this uncertainty, we looked at finite sample optimal hyperparameters. This is a sort of jump scare, I'm sorry, but you're not expected to understand this. It's just we calculated the exact finite sample bias and variance in a well-specified ridge DGP. So that's a pretty limited setting. Things have to be linear in X. And one of the things that we found, which at least to me was surprising, is you can actually construct DGPs where doing any debiasing hurts your mean squared error. In practice, in an applied setting, again, what you care about is getting a valid confidence interval. So you might debias even though it hurts your standard error. Like your point estimate is going to be worse, but you're going to get a valid confidence interval. So this is an interesting result. And it led us to say that this is a totally unsolved problem. Like, there are so many questions in how you do hyperparameter tuning in debiased machine learning. And I'm looking forward to doing more work in this area and seeing what solutions other people find as well. OK, so we just showed when you compare this to traditional undersmoothing, when everything's in L2 land, so when everything lives in a Hilbert space, these two things were the same. In lasso land, things actually look different. So a lasso outcome model is sparse. And what happens when you undersmooth a lasso model? You mechanically shift towards OLS, but you also add in, as lambda gets smaller and smaller, you're going to make this more dense. And the order at which you add in the non-zeros is the order at which these covariates are best at predicting y along your favorite lasso path. Beta hat OG doesn't work like that. It still shifts things mechanically towards OLS, but it adds the non-zeros back in a different order. It adds them in the order at which, for the selection model. So it adds the order in which the covariates are best at balancing XQ, or basically the order of the covariates that are most different between the two distributions, P and Q. This is also a classic result. So this is the double selection lasso idea from econometrics, if you've seen that before. So it was nice that we could recover that inside of the debiased machine learning setup. OK, so let me summarize. We had machine learning as biased because the residuals could be bigger than they possibly could be. One way of solving this is to just fit more. So make the residuals smaller, and you'll have less bias. And you get something closer to the unregularized estimate. The other thing to do is to correct for the residuals after the fact. And our result is that, in many cases, these can be the same. So our results apply very broadly. Again, I've been saying everything is linear in X, but X could be some crazy high-dimensional transformation. For the different outcome models you could use, our results work for ridge, lasso, kernel ridge, principal component regression, honest random forests, or ridge in like the last layer embedding from some pre-trained LLM. When D is bigger than N, the definition of OLS, again, is the minimum norm interpolant, because there's many different OLS solutions. So our results hold for the one that has the smallest norm, 2 norm. And the results that I've presented here are for the mean, but exactly identical results hold for any other linear functional. So the average derivative of your machine learning model, that's the one that I'm using in my macro application with the Iceland data. Our results also apply to that. And there's lots of other stuff in the paper. The appendix, I think, is over 40 pages filled with extensions. Extensions to sample splitting setting, non-negativity constraints, nonlinear weights. We have a very lengthy interpretation of the results in an empirical Bayes setup that I think is pretty interesting. And there are many downstream follow-ups. So we've been working on this paper for a long time, so in the interim, we've gotten new results. We have new results complete on multi-calibration, connection to this ML robustness literature, on the TMLE, which biostats people might be familiar with, and then there are other future directions that we think are promising as well, as well as to this sort of proximal causal inference literature where you're doing this exact same setup but with conditional moment equations. So I think that one's particularly interesting. So to convince you that this is a kind of useful exercise, I'm going to show you that we can use these results to get new results that can be like applied in real data. So I'm going to give you a sneak peek of a new paper that's coming out this fall that just directly uses the results that I just went over. I'll keep this pretty short, but we make a connection to the fairness/robustness literature. So in particular, there's this set of work on multi-calibration or multi-accuracy, and we showed that you can make a direct connection between de-biased machine learning and that literature. The paper is called Multi-Accurate Estimators Can Be Simultaneously Robust and Efficient. Paper to come out this fall. But this is the result that I just showed you in this paper, which is de-biased machine learning is equal to some plug-in outcome model applied to your distribution Q. But a natural thing that you might wonder is, what if we use that model elsewhere? So what happens if we plug it into another estimand, XQ1 or XQ2 or XQ3? And it turns out that if you're in L2 Hilbert space land, this beta hat aug is simultaneously semi-parametrically efficient for all of them. So by doing this debiasing once for Q, you somehow also did debiasing for Q1, Q2, and Q3. It is at least somewhat surprising because the debiasing step was supposed to be specific to Q. And I just ran into a wonderful application of this where I was estimating age profiles, where each one of these curves, I'm not going to tell you about the details of this setting, but every single one of these curves is a vector of estimands. And so normally I would have to go through and fit these debiasing weights for every single dot on one of these curves. And our new result means that you only need to fit once. You fit the weights once, you calculate this beta hat aug, and then you just plug it in across the whole curve. And so this applied paper is coming this fall. It's in an application to the so-called age-time cohort problem. People feel very strongly about the age-time cohort problem, so if you want to come argue about that, I'd be super happy to talk about it. But that's just a summary of our results plus a sneak preview of what we've done with it. So machine learning is biased, and it turns out this sort of undersmoothing type literature was equivalent to this de-biased machine learning literature in many ways. So I think there's going to be more results to come. I found this to be a fruitful framework to work in, and thanks for your attention.
Well, thank you, David, for the really excellent presentation with lots of interesting insights into old results and some really great possibilities for new ones. So in the tradition of the RSS, we will now move on to the vote of thanks. These are invited discussants. Each one will have 10 minutes to speak and will have 800 words in the journal. Sadly, due to travel constraints, our invited discussant hasn't been able to make it, so Lin Liu from Shanghai Jiao Tong University will propose the vote of thanks, but he'll do it by video. So hopefully we have that available.
Let me get started. First, I want to congratulate the authors for this exciting pedagogical and thought-provoking paper. I want to thank the organizer for the kind invitation, all the help behind the scene. I'm both excited and humbled to get invited as I follow the author's work so closely and look up to them in my own research. Unfortunately, I couldn't be there in person, but I very much look forward to watching the follow-up discussion and the author's response online. I want to summarize this paper in a nutshell. The paper is about low-dimensional functional parameters of high or infinite-dimensional statistical models. It's built on a large body of works in the past decades. For example, infinite functions in semi-parametric theory, double robustness, Neyman orthogonality, covariate balancing in causal inference and mixing data literature. So due to the large number of works, it's very nice to see a paper that synthesizes isolated concept tricks through the lens of linear model, which are familiar to most of the statisticians. Another key message of this paper to me personally is that it provides a new outcome-centric point of view, which can be have interesting implications. To see that, I will use the mean of the counterfactual mean of y under the treatment group under ignorability as an illustration. So this parameter has been studied a lot in the causal inference literature. Although I want to mention that the paper covers much more examples. Also, the paper presents everything using finite sample. I'm pretty sure the authors themselves also do that in the talk, but I will use population instead. I still want to follow the author's notation as closely as possible, so X will be denoted as d-dimensional covariates, Z as binary treatment, Y as the outcome. To estimate psi, it often involves two nuisance parameters. One is the MX, the outcome regression model in the treatment group, and then AX is the inverse propensity score. So with these two nuisance parameters, you can write psi as the mean of AX times MX and weighted by the treatment sum and Z. So in the paper, the author denote Z times AX as omega, which is the balancing weights in the covariance balancing literature. And since the nuisances A and M are unknown, a common exercise by statisticians is to assume they are linear models. Of course, here X can be replaced by some nonlinear feature map phi of X, which is done in the paper. So in my talk, I will denote the alpha twiddle as the balancing coefficients and the beta twiddle as the outcome regression coefficients. Particularly, I'm going to choose alpha twiddle as sigma inverse mean of X, beta twiddle as sigma inverse mean of Z, X, and Y. And the sigma is just the population gram matrix X weighted by the treatment sum and Z. With this linear model, you can still plug into the expression of psi, and eventually will be equal to this very nice bilinear form of twiddle transpose sigma beta twiddle. Also equal to the mean of the linear outcome model when you choose beta as the beta twiddle. Also, by double robustness, you can either replace beta twiddle by arbitrary beta or replace alpha twiddle by arbitrary alpha. You still have the same equality. And in the paper, the authors call this Z times of twiddle transpose X as the exact linear balance weights because after weighting the X by these weights and taking the mean, it's equals to the mean of X. So to see why I mentioned that the author provide a new outcome-centric point of view, let's start from an arbitrary choice of alpha and beta and plug into the parameter psi. So in this case, obviously it's not equal to the mean of the outcome model with beta twiddle anymore. But still, the author observed that you can still write down this expression as a linear transformation of X with a particular choice of beta. They denote this beta as the augmented regression coefficient beta. It's a weighted combination between the true beta twiddle and our arbitrary choice of beta. And the weights corresponding to the balancing weights on the beta twiddle and the imbalancing score on the beta. So this is in the proposition 3.2 of the paper. To me, this is the most important results of the paper. Why it's important is because it's making precise how the balancing weights change the outcome coefficients when you plug in a wrong balancing weights. Then the authors move on to from the arbitrary choice of alpha beta to particular choice of alpha and beta. For example, they choose alpha and beta to be certain regularized linear balancing or linear regression score, and then they can review certain connections between undersmoothing and the double selection, which are common phenomenon that we observe in the current causal inference literature. They can also use this formulation to get some exact bias and variance characterization and then help us to understand hyperparameter tuning in regularized linear model when applying to causal inference problems. So after I have summarized the author's main contribution, or a very brief summary of the main contribution, I have several questions. The first question is, I think implicitly the authors start from writing the parameter psi as a bilinear form between alpha twiddle and beta twiddle. How about the alternative representation, where you can still write this psi as mean of x transpose sigma inverse mean of z and x and y? Using this representation, you observe that only the nonlinear part in the expression is sigma inverse. Everything else is linear, so easy to estimate. So instead, one could simply compute a regularized estimate of the sigma inverse by some regularized inverse square matrix estimator. With this choice, we can construct a second order use this estimator by plugging the regularized inverse square matrix. After some algebra, you can realize that this second order use the estimator can be represented as a mean of the outcome regression model, but with the regression coefficient to be a leave out regularized coefficient estimator. You can do the same trick for the balancing part. So obviously, this kind of estimator has connection to sample splitting because lieu out is a kind of extreme form of sample splitting. It's also connected to the higher order inflow functions framework proposed initially by Jamie Robbins and colleagues. One disadvantage of this formulation is that this inverse regularized gram matrix estimator may be difficult to analyze, in particular if you are using the more advanced, for example, the Stan shrinkage estimator proposed by Ledoux and Wolf. But I want to mention that in our previous paper by with Rajesh Mukherjee and Jamie Robbins, we do observe some promising simulation results. An advantage of this formulation is that we have one less hyperparameter to tune, and it may motivate some more general regularization forms. My second question is why, when we do this regularized balancing, why minimize the L2 norm of the omegas? For example, in a high-dimensional sparse model, one could instead minimize the L1 norm of the balancing coefficient alpha. This can pursue sparsity or low L1 norm, which is more desirable in sparse models. This was implicitly done in in a paper by Professor Zhixiang Tan. In a recent paper by myself and my student Xinbo Wang and the colleague Wihao Wang, we also use such a balancing scheme to relax certain sparsity assumptions. I'm wondering whether the message in the paper can still be relevant when we replace the objective function in the balancing part from the L2 norm of the weights to L1 norm of the coefficients or some other objective functions. Finally, I have two philosophical questions or comments. Why outcome-centric? What if we do a balancing-centric viewpoint? Also, we can write down this psi alpha beta as a linear combination between the true alpha twiddle and the alpha. What's the potential implication of this exercise? And what kind of other lessons we can learn from these algebraic equivalencies beyond hyperparameter tuning? Whether it can motivate new estimators or even new hyperparameter tuning procedures. I'm really eager to learn from the authors. Finally, I'll conclude. Want to mention that the authors are really being modest in the paper. There's not a single theorem, but there's many insights. summarized in 9 propositions in the main text. There's a long appendix, but it contains a lot of gems, including comparison with TMLE, nonlinear balancing, empirical base, etc. It's a very general paper, even though it has linear regression in the title. But I want to mention that even if you are interested in non-parametric regression using a linear sieve or something else, these papers is still relevant to you. So with that, I will propose my vote of thanks and congratulate again to the authors. I really enjoy reading the paper and encourage everyone else to take a closer look. Thank you for your attention.
We very much thank Professor Lin for his comments. So we now move on to the second vote of thanks. This is Andrej Sarkar from the University of Ljubljana, Slovenia. He will now second the vote of thanks. Andrej.
Okay. Firstly, thank you to David, to the authors for a great paper. I was invited on a short notice, so hopefully my discussion would provide some interesting points. The role of the seconder is usually to be a bit critical, so you will hear more about the scope and some points, mathematical and others, in your paper. Like David already presented, like was mentioned by the proposer, so the paper is in general on the topic about how to eliminate bias in machine learning. Naturally, read the paper yourself. It is related to causal inference and machine learning. There have been recent papers already in this literature by David, by a few other scholars like Apurva Lal and Hido Imbens and others. So it combines how to avoid the overfitting problems and similar using regularization and the approaches that David presented using methods deriving from causal inference related to IPW, augmented IPW, and similar approaches. Thanks. So it's disappearing here. So David already mentioned naturally that this relates to Reed's representer and the, as you mentioned, Hilbert space and similar literatures. So it was already mentioned by the proposal. I think there are two main propositions, not just one. First relates this general balancing approach to the OLS regression. And the second one relates this even more deeper to the augmented estimator that you see here, where again, as David mentioned, you have a relationship to OLS that frequently reduces to OLS, and it relates, as you mentioned, also to convexity assumptions, which are interesting when you analyze this mathematically. It provides analysis for reach on L2 in L2 setting and lasso in L1 and affinity settings. And like also you mentioned and the proposer mentioned, a few other settings and extensions. So I will point to three broad strands of scope and other extensions. First is regularization the best way to approach the problem? So the authors relate to automatic double biased machine learning. Chernozhukov and other authors experimented with this. So it is naturally interesting to explore how to solve these problems of bias in machine learning. You already mentioned literature related to Berkeley University by Mark van der Laan and colleagues. So question is naturally how to tackle, how to approach this problem also in a different manner. This is the competing approach, but probably there are also others. And as you mentioned, also different neural network and machine learning perspectives. It would be great, because you're dealing with a bias in machine learning in general, how to extend this. You mentioned even last embedding of the LLM LLM, how to extend it to different neural networks, machine learning models to bias in such settings. Secondly, as I mentioned, your approach relates to causal inference settings. You briefly mentioned, you also mentioned proximal causal inference by Chetgen and other authors, recent literature that is developing. But for a causal inference scholars, it is naturally very important to know how would this balancing weight, augmented balancing weight results that you have extend to the general settings, say difference in difference, mediation, regression, discontinuity, IV, and others. So instead of just the general outcome regression setting, using such weighting approaches, also naturally most of those models relate to a potential outcome approach. How to extend this also to, we all know, the graphical approach setting on even to Swix, which surely you know are combining this. And thirdly, I might be more of a Hilbert space fan that you jokingly mentioned during your presentation. So for somebody working also in mathematical spaces in probability, and which is essential naturally and important to work with machine learning today, which extent we still don't know a lot how machine learning behaves in different probability settings. Your approach derives from reproducing kernel Hilbert spaces. They were mentioned on several spaces also today during the conference. But if you analyze RKHS spaces, you have kernel settings, and not just to mention to go into different kernels, which is one possibility. In real settings, you could also go to complex analysis settings, this is clearly probability, and to analysis which is unexplored, but would be very important to address in the explorations of machine learning, which relates to complex analysis with one variable and with several variables. I list just few possibilities of kernels in such settings, but at the same time note that this analysis for its several variables is still a complete blank in probability theory and stochastic processes. So to address this, it probably extends what you do, but it would be extremely important for analysis here. And to add, this is a high-dimensional setting, and today in probability, we discuss problems of dimensionality in different models, also yours, I would reckon, where you have problems in moderate dimensions. In very large dimensions, some limit results are known. In dimension 2, it's quite easy to analyze, but how about with these probability results in moderate dimension listed here? Maybe this could be interesting to explore. So to conclude, the contribution address is definitely a relevant problem. Novel results, it is naturally time-wise relevant to analyze both machine learning and causal inference, which have an intricate connection, they're always connected. To my opinion, I noted the role of the seconder, in particular in the scope you mentioned in your presentation yourself, David, at the end, novel possibilities that you explore. It is still somewhat limited, so I try to point it, how to extend it in future research. So I found the proposals in the paper very exciting and stimulating to discuss, and it gives me great pleasure to second the vote of thanks for what will surely be an influential paper. Congratulations. Thanks.
Thank you, Andre. So in the usual way, we want to thank both David and the proposer and the seconder for their excellent presentations. So before we open the discussion, let's thank everybody again. So we'll now move on to the open discussion. As I mentioned before, please do come up and talk about this paper. People are limited to a maximum of 5 minutes, but please feel free to come up and give a short or as up to 5-minute contribution as you would like. Please make sure you give your name and your affiliation because we would like to follow up with you so that you can publish a version, later written version for your contribution in the journal. These will be published alongside the paper and, of course, David's response to those and his co-author's response to those contributions. So I'd like to open the floor. Is there anyone who'd like to open the discussion? Well, while people are thinking about that, I'm going to invite Ben Swallow to come up. Ben is our discussion papers editor, and Ben will summarize a response we have already received as a written contribution from Charles Doss and Jared Wheeling.
Thank you very much, John. So prior to today's meeting, we received a written contribution from Charles Doss and Jared Wheeling at the University of Minnesota. I'll do my best to summarize this quite technical contribution as best I can. But the authors say we congratulate David and colleagues on their exciting paper. One case not investigated in the Brunsmith et al. Paper is when the treatment variable is continuous rather than discrete, and the dose response curve theta 0 estimated at z0 is the target parameter. If we then assume a non-parametric model for theta 0, the Riesz representation results no longer apply. Specifically, the semi-parametric information bound is not finite. Despite this, in what follows, we show the finite sample results presented in David's paper can still be made to apply, and that the resulting exploration suggests novel estimators. And they propose an extension to propositions 3.1 and 3.2 to the context of weighted least squares. And in their derivations, they suggest studying of variously locally weighted estimators of theta 0 that do not appear to seem to appear in the literature currently. So thank you very much for the contribution.
So do we have any other contributions from people on the floor? Please bear in mind that if you feel like you'd like to make a contribution but don't want to stand up and do this, we will still, of course, accept written contributions after this session. So I would encourage everybody to reread the paper, to write your contributions, to use up the 400 words that you have in the journal to be able to make a comment on this paper and submit that in time for David to then be able to respond to that in the usual way before all of the contributions are published in the paper, in the journal. It is the end of the day. So with that, if there's no discussions from the floor, I'd like to give David the opportunity to respond to the two discussants that we had, the proposer and the seconder, noting that this is entirely optional for David. He can say as much or as little as he likes, up to 10 minutes. And then he will, of course, be able to give a more considered reply when he reads the discussants' versions in the journal itself. But David, the last word is yours.
Thank you so much for the comments. I think I have way too many things to respond to. There's like 12 or 14 things that I just wrote down, so I'm not going to go through all of them. At a high level, I mean, both speakers pointed out that I'm saying this in a tongue-in-cheek way, but there's a certain lack of mathematical sophistication in the paper. Like, we intentionally didn't call anything a theorem. Everything was called a proposition. And I think part of that was because we were trying to be simple and aiming at clarity in a literature that's at the intersection of a million different subliteratures. So I actually saw that as a strength of our paper instead of a weakness. But it does mean that you can get more and more complicated in the follow-up papers. So I'll try to give a few comments on things I'm excited to look at next based off of what the discussants said. Let's say I'll do one for each paper. So one for each discussant. The first presentation said, this is a sort of outcome-centric view. Why couldn't you do a balancing-centric view? And I think you can. So there's this sort of fundamental flip-floppiness between being able to write debiased machine learning as debiasing the outcome model versus debiasing the propensity score weights. And I think you can just use exactly the same argument, flip everything, and do all of our results in balancing weights land. I'm not sure, I don't know what would happen. Like, it could be that like the result just looks exactly the same, but in the weighting form. But when you're in weighting land, everything is a kind of linear smoother, you know, and there's some ways in which these outcome models are also linear smoothers, right? Ridge regression can always be written as a weighting estimator. So that's one thing that we've always thought about as, what if we just flip-flop everything and run the same argument? And so I'm glad that someone brought that up, and I think I'm actually going to go try it. The second speaker, one of the things that I hadn't thought about before is trying to do this with something that's not a conditional mean, like a regression discontinuity. But one of the things that we have thought about is the extension to the IV setting. So the IV setting is a kind of pretty straightforward jump from a normal regression to a conditional moment model. And you can there's been lots of work on debiasing in those types of conditional moment models. The problem is you have different sets of covariates now for the outcome model and the weights. So the weights are going to be in terms of your instruments, and the outcome model is going to be in terms of your treatment. And so it's not clear exactly how those are going to get combined. So one of the things that we thought about a little bit, but we haven't really explored, is what if you just combine, you take the linear space that's just the concatenation of those two, and see whether or not you can run our machinery there. And then you'll have some type of sparse structure where some only use the treatment and some use the instruments. There is at least one paper that has done the double ridge, the ridge plus ridge equals ridge idea, but in conditional moment land. So people are kind of looking at this in IV, and I'd be excited about following up on that. But I haven't thought about, yeah, like a regression discontinuity also has some type of moment condition, and you could think about some type of debiasing expression there, but I wouldn't know what it would look like. Finally, for the last write-in comment, so the people who wrote in point out that, hey, there's lots of summaries of a machine learning model that aren't linear functionals, so they don't have a Reese representer, and our results totally don't apply in those settings. So they gave this example of, what if you just want to estimate a dose response at 0? So you have a whole dose response curve of what's the causal effect for different levels of some drug, and you want to estimate it at the point exactly 0. You don't give them dose. Well, that's not a continuous functional. We can't use our type of machinery. But it sounds like that the people writing in already have new results, so I'm looking forward to reading it. I haven't seen it yet. That's all I'll say, and it sounds like we're going to have a lot more to respond to when we actually write for the journal, so looking forward to that. Thank you.
Thank you very much, David. So we have two upcoming meetings. We have an online-only meeting on the 8th of October with a Series B paper by Whiteley et al. And we have a hybrid meeting at the Hallam Conference Centre in London on October the 22nd with a Series A paper by Chattopadhyay et al. Both papers can be found with all the other details of the discussion meetings on the RSS website, and will also be announced in members' newsletters and on social media. And I hope you take a look at those papers and contribute to those discussions as well. But I'd just like to close the session with a huge and special thanks to the authors of the paper, and particularly David for coming to present it, and to our discussants today. RSS discussion meetings and papers are really a special part of the society, and I'm so grateful that they've taken part in one of these today. So let's thank them all again.